And so more solutions. So we're on, and we have page numbers, and they're really random page numbers because I think the next set of notes starts at page 41 or something. There was a reason the notes had pages at one point. You used to have to go and buy them in the bookstore. And so there were study sets and labs in the whole thing. So you got a whole packet with stuff. Lots of fun jokes. I did want to mention something before I begin. And that is that you guys have another class presentation. And it is week 8, as I corrected my thing here. So the end is near. 3 weeks from today is our last celebration. And then we're all free to go, which means we have to do the presentations before then, which is in the next 2 weeks. So on our syllabus, it has us doing them next week. We can talk about this more on Thursday. I originally wrote the syllabus, so we did them before Memorial Day. I'm not attached to that. I'm willing to do them after Memorial Day, but we have to make a choice by Thursday. If you want to do them next week, we can do it. And then you don't have to worry about it over Memorial Day, or you can do it when we come back. I would have assumed you want to do it before Memorial Day. But so look at your schedules with all your classes, and which means if we're doing them next week, you guys have to come up with topics. So the lab you just did on plastics, you all had to write something. So some of you had some really cool stuff. So you're going to be, this is innovation. The previous lab on gas laws was actually even more interesting. A lot of you found some really cool innovations with gases. And then the lab this week, which I know I didn't post yet because I have to make a video that goes with it. And I was in a grumpy mood yesterday, not in a grumpy mood today. So I will be making the video first thing tomorrow morning and it will get posted. It is a kitchen chemistry lab. And then there's also math. You get to do a problem solving of my I give you like this. It's like a worksheet and then some kitchen chemistry. And then you get to do another 1 page. This is about water solutions and mixing stuff in water. So you get a choice of either something to deal with cleaning up water pollution or safe drinking water, because a lot of people on this planet do not have drinking water that is safe. And there's some really cool stuff they're doing of ways of collecting rainwater and stuff like that. Or desalination of water. So, right, most of the water on the planet is salt water, which we can't drink. And so that's actually a big thing. There's also a talk I listened to today. And so if you're somebody going to the health fields, there's this thing where you can magnetize water and it changes its healing properties. There's actually a lot of really cool innovations with water. Water does a lot of really cool things. So you can also pick a different innovation, but it's supposed to be something related to this term. So you can send me an email, but we will need topics and we will decide by Thursday, or if somebody wants to make an opinion today, you can email me that, yeah, you want to, I should have put it on the worksheet for Thursday, or the worksheet for today. Maybe you should put it on your worksheet, but look at your schedule because you all know if you're going to get really busy after Memorial Day weekend. All right. So this is the page that's words. This used to be the first page of the notes, and I learned that starting with all the words can be a little bit much. And then we go back and we're going to review the math. And then I have a new piece, one more dimension we have to add to this. So the parts of a solution are what? This is where I have to find my markers. Anybody? We can get you all up on the board. Major's like the only one up there right now. And actually, you know, Damon and Tristan aren't here tonight, so you guys have lots of good chances because they won't be butting in with the answers all the time. Nobody wants to tell me the 2 parts. It's an easy answer. It's like such an easy piece.
Solute.
Yeah. You're a little too slow there, Max. You have to wait. I'll catch you on the next one. So it is that there's the solute and the solvent. And so almost always the solvent is the major component. What is the one exception to that?
Water.
Yeah, H2O is always considered the solvent. That's probably part of why it's considered the universal solvent, even though it's not. Solubility is how much dissolves. And for those of you who are going to be taking Chem 223, just these were some other questions some people were asking me. Chemistry 223 is 5 weeks. It's condensed. It's the second half of the summer, so we all get 6 weeks off from each other. And that is because some people are currently in Chem 221 and they'll take 222 and then they'll join us. So it should show it's starting July 26th to August 26th. It meets 4 days a week. There's 2 different sections. If you have a question, you can ask me. The afternoon section will run like this one. So from 1 to 3 every day, we'll go over a study set and we'll do lecture. And more than that, haven't thought that far. I'm more worried about getting through this term. But in 223, we actually do spend 2 days, because 2 days is a week in the summer, on the mathematical computations of solubility. There's a whole chart that you get, and we go through it. It is not predictable. It has to be done experimentally, and so somebody made a big chart having done the experiments. These terms, though, are important. So saturated is when you have the maximum solute dissolved. Oh, that's really funny. I hope the rest of you aren't feeling left out. I got Major's name on here and Max's name on here, and I really don't know how I can get anybody else's name on here. I've never had that happen before because I've never had names where I get to use them in my definition. Everything has, and this is temperature dependent. We get down to that later. So with that, unsaturated means that you're less than the max. And supersaturated, this is a really fun lab that we used to do. Supersaturated is more than the max. You have to somehow trick the solvent to get more dissolved. So if any of you ever as a kid, or maybe now as a kid, you can go buy those kits that have crystal making in them. And so you'd put the stuff in and then you'd sit there, like you'd microwave it and then you'd let it sit there, and the next day suddenly crystals would start forming. That was a supersaturated. Or when you get the hot or cold hands, so if your hands are always cold, you get those little hot hands. That's actually, some of those are supersaturated solution, and when you disrupt it, like you have to do a snap thing, it disrupts the solution, and as the solute comes off, it's exothermic, it releases heat, and it warms up your hands. Everything has a specific saturation point, so you'll either be given a number, and if you have more than that, it's supersaturated. If you have less than that, right? Another way to do it would be just if we added solute. If you're saturated, the solute will not dissolve. It will just float to the bottom or sink to the bottom because it's already saturated. You can keep stirring and stirring and stirring, but it's like you add one more cube of sugar and nothing's going to happen. That sugar is not going to dissolve unless you make some other change. If you were unsaturated, yes, it dissolves. If you add solute, it will dissolve. Because there's still room for it. So there's still room for more to dissolve. And the thing that's really cool is if it's super saturated, is if you add solute and it's already past the max, you will pull out all the extra. So you'll actually get a whole bunch of crystals coming out, not just the one piece you added. So if you disrupt a supersaturated solution, it just comes out of solution. And we'll probably see homework questions with it, and that will like fine tune it. All right, the next question is what your lab is about this. So this is lab 8, which again, I will have posted by tomorrow morning. If somebody's like eager to start it, you know what, you can do your whole study set and worksheet for Thursday. You guys aren't like my other class. You tend to do everything the day it's due. I can have office hours Saturday, so we can negotiate that on Thursday. So yeah, so this Saturday I will have office hours because of the lab that will be due Sunday, or you can always just email me. And again, you can always submit, if you get the lab submitted by 6 o'clock on Sunday, I will give you feedback and you can resubmit it. I fell asleep this last Sunday at 6:30. Teachers get pretty tired this time of the term. So that's why it's a 6 o'clock. Sometimes I'm up till 8, but all right. The rule for what dissolves what, does anybody know? We've done it this whole term. It's been like the central theme tying in the whole term. Polar likes polar. So things that are polar mix together. Things that are nonpolar mix with nonpolar. So they will often say like, likes, like. It's kind of silly. It's like a little kid thing, like, likes, like. So polar likes polar, nonpolar likes nonpolar, and water again is polar. So we're looking for things that are similar. If you see something that's polar, this guy H bonds, and so does water, these guys are going to dissolve. They like each other, definitely. So that's methanol and water. So the term, by the way, miscible, means that they mix. This is a fancy way of saying two things mix. So sometimes it will ask, do they dissolve? And sometimes we'll say the word miscible. All right, how about on B? B gets frowny face. How do I know C8H18 is nonpolar?
It's London.
Yeah, and what I was looking for, it is London.
Carbon and hydrogen.
Yeah, it's carbon and hydrogen only. So things that are carbon, hydrogen, this is an oil spill. So if you have the octane from your car, it gets water in it. They do not mix. Right, the next one, they like each other. So they're both nonpolar. If they're only made up of carbons and hydrogens, they will definitely mix. So the organic chemistry, when we talked about it, these are the hydrocarbons. And then our last one on D, anybody? Nope. Why?
Because one's polar, one's non-polar.
Yeah, so that's a simple answer. Yes. So that one H bonds, or it's polar. And this one is non-polar. So oil and vinegar don't mix. The way you mix them is you need something. Can we put it? We can put it up here. There are things called emulsifiers. And that was the word everybody used for hundreds of years, was emulsify. A new word has shown up, but an emulsifier is polar and nonpolar. So an emulsifier is truly a universal solvent. It likes everything. Water only likes things that are polar. Another thing though about water, water also likes ions. So we've known that because of the polarity. So an emulsifier is something that has both parts. An example of an emulsifier is, well, what they put in all your food is lecithin. So lecithin's an emulsifier. I think I have a picture of it in the slideshow, but a simple example would be this guy. So if you can see that, that is acetone. This is what's in fingernail polish remover. A lot of people will have it in their garage for cleaning things because it has the carbon chain, but it has the oxygen. So it's going to work with both. we don't want to add acetone to our salad dressing. So how they get the vinegar and oil to mix in salad dressing is lecithin, which is found in egg yolk. So egg yolk has water. It also has cholesterol, which is nonpolar. The thing that's fascinating is a new word showed up. I never saw this before until this year. And so Google is wonderful that these words can show up. And they call this, and I think I've mentioned it before, you know, I found my missing pen, and I think now I know why it was missing. They call it Amphiphilic. There's different ways they spell it. I spell it like this. So amphi means all. So like an amphibian could live anywhere. Phil, city of brotherly love. I'm pretty sure I talked about this in the organic lab. So it loves all things. And so it would be something has a nonpolar and a polar component. And so it dissolves everything. And so lecithin is a good one. I have some examples, and there's some questions on the lab where you look at pictures and decide if it's polar, nonpolar, or amphiphilic, where it loves everything. Just another quick reminder, when something's polar, what's the other word we say for something that's polar, that loves water?
Hydrophilic.
Yeah, hydrophilic is something that is polar because it loves water. And what's the word for something? You know, Damon's going to be watching this video later, yelling. He's going to be yelling to the camera. Somebody answer her. Somebody's going to answer. Go ahead.
Said hydrophobic.
Yes. Yeah, I was going to say somebody who's in biology has to know that because those words become ingrained. So something that's non-polar, that has absolutely no oxygen or anything, is going to be hydrophobic. Hey, you know, the extra points add up. Some other people, maybe I only have 3 people in class today. It's like the sun came out, everybody just is there on Zoom and they disappear. It's probably why all the chemists put that we want to be back on campus. All right. So more terminology. There are 3 different types of mixtures. So a mixture means you have a solute and a solvent. It's not a pure substance. Solid, liquid, gas are pure substances. They are not mixtures. The difference between these types is the size of the solute. That's really the big piece. Solution is an itty bitty, itsy bitsy, teeny weeny solute. We're talking solute. So these are like a nanometer in size. You don't need to remember the number or anything. They're just really little. You're not going to be able to see it with your eyes. So an example would be salt water. You can't see it, and it cannot be filtered. It's too small to filter. So it would go right through a filter. To separate it, you would have to do something like heat to heat off the solvent, and the solute's left behind. And that's what like this picture over here is trying to show. All right, a colloid is actually where we have small solute. This is like micron size. So a colloid, example of a colloid is milk. So the solute, we can't see it with our eyes, but they're larger molecules. So they're usually like large molecules, like proteins. And our blood is, not our blood, our plasma is a colloid. Jello is a colloid. Fog, that was the other one I was looking for. Fog is a great example. And colloids do something that's really cool. And that is they do something called the Tyndall effect. It is spelled with capital T because it is named after a guy who observed the effect. And where we live, you have all seen this. If you go to the Oregon coast, if you go to the redwoods, like one of the most amazing places there are, the fog comes in. We get it here. Sometimes we'll get the fog, not as much, but if you drive through a fog with your headlights on, they don't work, because what happens, these particles are big enough that they scatter light. So the solute scatters light. And so if you go to the Oregon coast, there's always like this morning fog, that mist that comes in, and it scatters the light. And so you get these really mystical pictures. Everybody's possibly seen it. If you try to drive your car in the fog, your headlights don't work because the fog makes your headlights go to the side. You can try shooting a laser through milk and it will not go through milk because the protein or the fat makes it divert to the side. If you take salt water, the laser beam is going to go right through. And so that's just kind of a cool effect of it. And so I think our plasma was the other one I mentioned. So if you take the cells out of our blood, so the plasma is our blood with no cells. So it's the blood fluid with no cells. The cells are too big, and so that's our last one. The suspension is large solute. And so this would be like really big, like the size of cells. Best example here is mud, paint, or your blood. So if you take a sample of your blood, you don't have to try this at home, and you let it sit in a test tube, it actually will separate, because the red blood cells and the white blood cells will separate out from the plasma. If you think of mud, so we've had a few showers. Hopefully we actually get rain this week, but that mud will settle when the rain stops, right? The dirt settles. Paint, when you get it, they put it in a machine that shakes it for a half hour. And then if you have to touch up like a year later because your cat scratches his neck on the edge of the paint or something, you go to touch it up and you open the paint can, everybody's always like, "Ooh, what happens to my paint?" And nothing happened, you just have to stir it. And so that is one of the qualities that you can tell you have a suspension, is it settles or separates. You can also filter it. And so if that's one of the big things with cleaning water. So the problem is it's a lovely way to get rid of large cells that might be contaminating the water, but if it's something that's like viruses are too small, they won't be filtered out and stuff. All right, but boiling water will kill them. This is our next two pieces. And again, I said the words, we get through the words. One page of your study set is all the words. This is actually a gas law. And so it's going to look like a gas law. I'm going to just put S for solubility. And actually, so you can do actually mathematical thing, but we're going to, as you increase the pressure, you increase the solubility of a gas. So something I did not mention, we can go back up here. The solute can be a solid, liquid, or gas. So I've been implying that it's always a solid, but you can mix a liquid or a gas. The solvent can also be a solid, liquid, or gas. You can mix and match any way you want. So an aerosol can, that is a gas mixed with a gas, but you can also have a solid mixed with a gas. Air is a mixture. So here you can increase water. The streams in our water is obviously a mixture of tap water. There is oxygen in the water. And so the amount of oxygen in there, if you get champagne or soda, soda has CO2, as does champagne in it. And we increase the pressure to keep the bubbles in there. And when you open the can or open the bottle of champagne, the pressure changes, the pressure increases. Sorry, the pressure decreases on the outside and all the bubbles come out. So the gas solubility. And so it would just be a relationship. It's just, I don't do math with it. The temperature one is actually a global warming issue. So as you increase temperature, you decrease the solubility of a gas. And so this is actually a problem we have since the temperature of water has increased. Now, global warming is looked at very much in a one-dimensional thing. And so if you really start Googling and looking, there are other factors that are happening that will give you a different perspective. But having been, like I've talked about, in Nepal and Tibet and seen that the glaciers are pretty much disappearing, it's pretty devastating. But the temperature of like the small streams has especially changed by a couple degrees. And that means there's less oxygen in the water. And so the fish can't actually get to their spawning grounds because there's not enough oxygen for them to make it there, which becomes an issue. All right, that is of a gas. It actually will increase the solubility of many solids. So if you drink tea or coffee, if it's cold, you can't get as much sugar, solid sugar in there. High fructose corn syrup is a liquid, and so it was a wonderful trick of a way to get even more sweetness into all of our liquids that people like to drink. High fructose corn syrup is like extremely pernicious evil because your body doesn't recognize it. It's not natural, even though they get it from corn. It's so highly processed. Everything works by vibrations. The whole quantum class we talked about, everything's based on vibrations. High fructose corn syrup, your body doesn't know what it is, and so it does not use it. It stores it. It doesn't get rid of it. It just stores it as fat. And very different from honey. So honey's made up of fructose and glucose, just like high fructose corn syrup, but honey has the perfect vibrations. Your body never stores honey. Your body uses it immediately as energy. And it has to be real raw honey, unfiltered from the farmer's market. But anyway, so cold beverages, usually they have to do a trick to try to get all the sugar in them, which is make it a different type of sugar. All right. When you do the study set, answer the questions as best you can, and we'll refine that, all the word stuff. So we're going to review our units, and then we'll do some math. All right. Mass per mass. This is grams of the solute over grams of solution, or total grams, times 100. So the M per M means grams. Mole fraction is the moles. Could be the solute or the solvent, but we'll say moles of the solute over total moles. Again, this one, you don't multiply by any number. All right. Molality is our moles. Look at that. Everything's all about the solute. Moles of the solute over what? I'll say kilograms of solvent. So reminder, you can't abbreviate things as SOL because everything, we have a solution, we have a solute, we have a solvent. So this is like your nice little place where you have your formulas. You're going to always state your formulas like we did when we did our study set. Molarity, which is capital M, is moles of solute. That's why they're both start with the word mole. So you don't want to just say any more mole or gram. You have to have it fully labeled. And this is over liters of the solution. So the thing that's interesting is the denominator is always the whole solution. The exception is this one. Molality is just the solvent. Molality has a niche use, which is for freezing point and boiling point. Mole fraction is used for vapor pressure, and molarity is used for osmotic pressure. but they're all units of concentration. Molarity is by far the most common one. We saw it in Chem 221. We're seeing it now. And in Chem 223, it's pretty much a central theme. We use it all the time. It is the most common unit out of chemistry class that you will see. All right, density, it is grams per milliliter typically, or grams per cubic centimeter. It has to be the same thing on top and bottom. So it could be solution over solution. It can be solute over solute. It just has to be, these two pieces have to be the same. It cannot be mixed units. So density is not a concentration. The other ones are, because they're how much solute is in something. Density is not. All right, so we're gonna look at some assumptions we will make, and all right. So on this one, this is the piece of information we're given. Silver nitrate, anybody know the formula?
AgNO3.
Yes. So AgNO3, so nitrate is Nick the camel, and silver likes to be a one charge, so AgNO3. This little m means we're dealing with molality, that we're dealing with this unit. So the key is the assumption. For molality, our assumption is that we have 0.454 moles of our solute of silver nitrate, which is our solute. I'm just writing that to clarify. And so notice I'm not writing it as a fraction. I'm splitting it into two pieces. That is the key to make your assumption, because then you have to take what you need from there to figure out where to go. All right. The other piece that we must have is that we have 1 kilogram of water. It's our solvent. Since I do not state the solvent, it must be water. Those are the two pieces of information. So again, we start with the percent. You have this much, and the total is 100. Here, it doesn't work that way with molality. These are the two pieces we have. Now, you should be able to solve. So you're going to solve for percentage, and you're going to solve for mole fraction. So we're going to take a break in a moment. I just want to give you a hint of how to try these so you can play with them. ppm is parts per million. So on the study set, we did parts per billion. Parts per million is that you have so many grams of the solute, and it's basically like a percentage, but you're thinking of it out of a million. So you would have grams of the solvent or solution. This is the piece I need to mention, and then times a million. So it's like parts, it's like percentage. Percentage is parts per 100, parts per million, parts per billion. You're multiplying by a million or a billion. Because it's so diluted, the solute is so minor, you can assume that the solvent is the solution. You can only do that with ppm and ppb, so parts per million. And it's because you have so little solute. You can't do that with anything else. So on these other two, on 3 and 5, there's going to be a funky subtraction step. You cannot do 3 and 5 necessarily completely factor label. Actually, 3 you can. 5's going to have a funky subtraction step. All right, let's look at our assumption for number 5. So on number 5, you're going to solve for molality and you're going to solve for percent. The information given is molarity. And we have toluene. And this time I don't tell you, but the word dissolved in tells you the benzene is the solvent. So the toluene is dissolved in, so the toluene is the solute. They're both nonpolar, so water would not work as the solvent here. All right, this is the density of the solution. That's going to be important. The assumption we're making is from the molarity, that you have 0.21 moles of the toluene, C7H8, which is our solute. And what's the other part of the assumption? Does anybody see it? It's molarity. What's the other piece we know? If we have that many moles, it would be that you have 1 liter of the solution. So this is very different from this one. On this one, we actually know how much of each part we have. We know how much solute, we know how much solvent. So you just take the parts you need to know. On this one, we know the solute and we know the solution. How much solvent do we have? That's what you have to figure out to be able to do this, because in molality, you have to figure out your solvent. So I'm going to pause for, I'll start again at 10 after, so you can take a break or you can try working on these and yeah, come back in 8 minutes. All right, let's go ahead and go through this. Don't get me started on what's going on.
Sorry.
So again, the assumption. So your study set for Thursday, the first page is, and it's making the assumptions, the same with the worksheet. It's just labeling and clearly stating your assumption like I did here. I wrote solute and solvent just to make sure you could follow. When you do your math, just state your formula. So we're going to need grams of the solute over our total grams, or grams of the solution, whichever way you like to write it, times 100. So we have 0.54 moles silver nitrate. We will need to change that to grams. So again, label your setup, and just hold on, I have to find my numbers. This is going to be around 169.9 grams per mole. And then we divide by the total mass. So whatever that number is, yeah. So that turns out when you multiply that, that's 77.1 grams of silver nitrate, plus our 1,000 grams of water. So a kilogram is 1,000 grams. Just label it. So please don't just say 77.1 plus 1,000. Please label all the parts. I don't know if I've said that enough, that you need to label. So I had a student, it was a male student, like 6'4", and he came to me for help. And I'm like, well, you know, you're getting to the answer, but nobody can follow your work. There's no labels. And he was just like, oh, I'm going to make it real pretty for you for the real thing. And I'm like, just make it pretty as you're going along to begin with, so you don't have to redo it. But you can use his motto too, times 100. And it makes sense. The solute should always be the minor component typically. So 7.16%, sure. These numbers are all over the place. Like on the worksheet, it's less than, oh no, that was a different one. Might be on the next worksheet. One of them's less than 1%. All right, we're doing the mole fraction. And so we're going to do moles of solute over total moles. So the good news is we already know the moles of the solute because that was our assumption. So 0.454 moles of silver nitrate. And then 0.454 moles silver nitrate again, plus, notice there's parentheses. We have to figure out how much water we have. So we have 1,000 grams of water, and water is around 18.016 grams. You're going to divide by that number because you have to change it to moles. and you'll punch that in your calculator. Again, I like to do them in one setup. And what I see is about half of you are good with setting it up like this. And some of you, you'll want to find the number. You can figure out this number and write it underneath and then add it up. That's kind of a personal preference. All right, questions? Keep going. So we're doing parts per million. So we have 83.5 grams of silver. And then a metric ton. Does anybody remember what a metric ton is? A metric ton is a megagram. So 10 to the 6 grams. It doesn't say per water. So you can decide this is water or the solution. Again, that works only with parts per million, parts per billion. Because if you have a million and you subtract out, so let's say Major gets a really big tip, somebody gives him $1 million, and he's like, well, here, and he gives his coworker $83.50. Major still has $1 million because he really, but his coworker's thrilled because an $83 tip is a pretty big tip. And then you multiply by a million, which is kind of funky. All right, so that's where I get 83.5. The unit is ppm. Another way of saying part per million is they will often do milligram per kilogram. So some people actually learn it like that, or if you look online, because the difference between a milligram and a kilogram is a million spaces difference. So some places will do milligrams of solute over kilograms of solvent. The second one I wanted you to do is molality. So we want to do moles of silver over kilograms of water is what we're solving for here for molality. So you would just change your silver to moles. It's just silver, not silver nitrate. And then this was 10 to the 6 grams of water, so we just change that to kilograms. So divide that by 1,000. And we're going to get a really small number because parts per million and parts per billion are used when it's very diluted. So little solute means very diluted, very, very diluted. And talk like they do in India and Nepal, they repeat. The Bible does that too, which is fascinating to me. All right. Questions? All right, the next one's a funky one, but we got it. I'm wearing blue today for, it's my rain dance. We need rain. My plants are really happy when it rains. All right, so this is how much solute. So for this, I need my moles of my solute over the kilograms of my solvent. So what we have to do before we can plug in here, we have to figure out how much solvent I have. So my first step is, and number these, I have 1 liter of the solution, which, right, 1,000, 10 to the third, sorry, a liter is 10 to the third milliliters, or a milliliter is 10 to negative 3 liters. And we know the density, so 0.876 grams per milliliter. So you punch that in, that gives you that you have 876 grams of the solution. So you don't label it as 876 grams. So the other piece we have to do is, I'm going to write this over here. Well, we'll leave it there. I'll label it step 2. So I have 0.21 moles of the C7H8, and I can change my moles to grams by adding those up, which this is around 92 grams per mole. So the 7 carbons, 8 hydrogens. I'm pretty sure you all can do that without looking at a periodic table now, unless you think that carbon is 16 or something weird that we all do. So this comes out as 19 grams of the solute. I had to do that because my third step here is that I need to take the 876 grams of the solution, subtract the 19 grams of the solute, and we will have 857 grams of the solvent. That's the only way we can isolate the solvent. Look how nicely that's labeled. You guys can all follow that, right? My steps, I numbered it. Now I can go back and fill in over here. So the moles of the solute I already knew was 0.21 moles C7H8. My solvent, you would take your grams and change it to kilograms. So just out of simplicity, I will move my decimal place, kilograms of the C6H6, and you'll get my answer, 0.24 molality. For molality, this was a question somebody asked me earlier. You can either just write the M like that, like I did here also, or you can write moles per kilogram. That's a personal preference. It doesn't matter to me. It does have a unit. What's the only one that doesn't have a unit? What's the only unit that doesn't have a unit when you write the answer? It's a unitless unit. Go ahead.
Mole fraction.
Yeah, the mole fraction. We did that one up here. It's just a number. But since we have it in this nice line, you can kind of follow it. All right, so show your work. A lot of you, a high majority of you are going to be taking physics next year. And the physics teachers always come back and thank me because I've broken you in. The other chemistry teachers are right now warning their students, oh, you're going to have Sherpa this summer. You better learn how to show your work better. So I'm breaking you in for the other teachers. They'll be grateful. All right, percent is grams of solute over our total grams. Or you can also think of this as grams of the solution. And so we figured that out over here. So we just had to take our pieces. We have 19 grams of the solute. You can call it solute or C7 over. We have our 876 grams of our solution times 100, and we get 2 sig figs because we had 2 sig figs. Percent's our unit. Percents can have more than 3 sig figs. So on the worksheet, you end up with 4. And just a reminder, like up here, these zeros are placeholders. They are not significant. So this does have 3 sig figs. But on the worksheet, on question number 1, you're going to get 4 sig figs. All right. Any questions with that page? You can always go back and rewatch that part of the video. Take a screenshot. I don't know how to do that. All right. One more page. And then you can also just doodle on the back. There's nothing there. I did post the notes for Thursday is on kinetics. So we're going to be starting kinetics. And those notes are for Thursday and next Tuesday. And again, we're trying to decide when we're going to do our class presentations. I don't see that we're going to be ready next Thursday. This kind of jumped up on me suddenly fast. But if you guys all think you can be ready next Thursday, we can do them and get them done before the long weekend. I don't care. You can also do them. We have to do them in the 10th week, if not the 9th week. Just can do the 10th week. We can do them on the last day. We can do them on the Thursday of the 10th week if you guys want. So you can just like have that hellish 10th week when you have all your stuff due in all your classes and just that's what you all know that, right? All right. So vapor pressure is anybody whose name's not on the board? It's like Max, Major, and Christian. I don't know if anybody else is here tonight. I mean, your names are there. That is so funny. Maybe in the summer we'll get some new people who are going to participate. There's a couple of you who usually say something, but you're quiet tonight. So vapor pressure is how much solvent escapes. So I want to make, so to gas. I do want to make a comment here. On your lab, there is a problem like this. If the solute is volatile, anybody, what's that mean? It means it escapes also. Means we use a slightly different formula. So this is why a lot of times you assume that the solute doesn't escape, but if the solute, it also escapes, and so you end up with the P total normally, right, would equal X of the solvent times P of the solvent. You gotta write small to put this in. If it escapes, then you also have X of the solute times P of the solute. And so it's not on the worksheet, it's actually on the lab that you have to actually add the two parts together because they're both escaping. But the effect it has is as you add the solute, you decrease the vapor pressure. Sorry, I moved my hand. It gives you this formula in the lab on that question, and you'll know because it's going to give you like a lot of information, and you just have to figure out the parts to put in there. And so I'll have an office hour Saturday morning to figure out what time, which I think has to be at 10 because I think major you end up working until 10. And I think if I did it earlier, you guys would all still be asleep. Except maybe not Max, but I think the other, I think 10 o'clock's too early for most of them, but the reason why when you add the solute, you decrease the vapor pressure because higher IMF, less escapes. All right, so freezing point and boiling point, again, we just did problems with these. For freezing point, what happens when you add solutes? It decreases, boiling point goes up. Anybody remember why? Or I should just say Max Major or Christian, you remember why? Okay, when people go and watch this video, they'll be like going, I know why. It interferes with the crystals. So freezing point is all about making crystals solid. Boiling point goes up because you have higher IMFs, so you need more jiggles and giggles. Giggles are good for you. Keep giggling. All right. Osmotic pressure. We talked about this. Anybody? Osmotic pressure? Give you a chance to catch up. Osmotic pressure is the solvent moving. This is all about attraction. Solvent is attracted to the solute. So it moves to where there is more solute. It's attracted to it. So it's not a narcissist. It's not attracted to itself. It's attracted to the solute. I don't know. I meant here, what is the effect on osmotic pressure? If you have more solute, you have a greater osmotic pressure. So it's a pulling. The solute is pulling the solvent across. All right. This is pretty cool. So for those of you taking Chem 223, one of your class presentations is on a famous chemist. I don't know that anybody's picked him ever, but Bondhoff. And then the other one is you could do a chemical demonstration. which actually was really fun last year. I'm actually hopeful that by August that maybe they'll let us go on campus. So the people who want to go on campus, you'll have a different choice, which is we used to have some really fun labs in 223. It's like putting it out there for the universe. Again, it would be an optional thing. People who didn't want to go on would get to do other things. So the very first Nobel Prize in chemistry was this guy. And it was for this idea, I have to think what it was for. We're going to see the third Nobel Prize in chemistry on Thursday. So that was Arrhenius, or on next Tuesday. But the idea of electrolytes are ions. So you've all heard the term, right? Because that's the whole idea of Gatorade or all those different those drinks that have a lot of electrolytes in there. Keep your electrolytes high. Oh, I'm feeling faint. I don't have enough electrolytes. You're always fine. All right. So they're ions. So there is something called the Bondhoff Factor, which is just a little I, and this will be given to you. So if you look at the problem we're going to do, and it shows up in the next study set and worksheet, if an I is given, the I stands for ions. So if not given, assume it completely ionized. That is what we've been assuming all along. So I'm going to skip down to number 4 first, and then I'll come back and do the one with the I. So what I mean by completely ionizing is that we are assuming when you put sodium chloride into water, that it completely splits into sodiums and chlorides. So you have 0.5 molal of sodiums and 0.5 molal of chlorides. And that's why we multiply by the 2 ions. So you really, since you have 0.5 of each one, you really have 1.0 osmol. That's what I mean by completely ionizing. You just factor in how many ions. Calcium chloride, we assume it completely splits into calciums and 2 chlorides, so 3 ions. This is also what I mean on the very last question on your worksheet by labeling your work. So you have to show me where your numbers are coming from. So you just say there's 3 ions here. There's a calcium and 2 chlorides. So there's a calcium plus 2 chlorides. So we're just adding them up. So this would be 1.8 osmol. Potassium nitrate is just 2. So there's a potassium and a nitrate. So remember, polyatomics, they don't split apart. You have a potassium and a nitrate. So we would multiply by 2 ions. So we'd get 0.8 osmol. Pure water is 0. There are no solute. If there's no solute, you have no concentration, because concentration is always solute over something. This one, there's no ions. So if it's non-electrolyte, it is just still the same number. How can I tell that's not an electrolyte?
It's covalent.
It is covalent. It's it's the organic molecules. So this is covalent. It's a molecule. So whatever number you have, that's what you get. All right. The term electrolyte, it came from that it conducted electricity. So Bondhoff was around right when electricity was discovered. And so they were doing, and so he came up with this idea. This assumption is not true. They don't quite ionize enough. And so that's what the I's are, if you're given them, that you say, okay, it actually we didn't multiply by 2, we actually would multiply by 1.85. So when we solve this, we'll go through that. I want to go ahead and finish 4, else I'll forget. So which one has the lowest freezing point? It's going to be the same one with the highest boiling point. So that would be the calcium chloride. It's the highest boiling point, lowest freezing point. So the more you add, the lower the freezing point, the higher the boiling point. The pure water is your starting point. So this would be your highest freezing point and your lowest boiling point. Because it didn't change. All right. These two would come out the same because they're the same number. All right, we're going to do no, we're not doing osmotic pressure. We're going to do freezing point. So usually on these problems, we're just getting a rough estimate so we don't deal with I's. On the problem solving, an I will be given if it is an electrolyte. And so we see an ionic compound. I usually make ice cream for you all on this class. You can see in the study set, there's a lot of ice cream questions. So usually we make ice cream with liquid nitrogen. So something else you're missing out on. I usually make ice cream every term for you. And so we'll see. And I make it vegan. So I make it with avocados. I know it sounds weird, but I think avocados and some kind of like coconut milk. And yeah, I usually make strawberry rhubarb because it's rhubarb season. I usually have to go and find somebody who has rhubarb. It is so good. No, you might be looking at me like, ew, avocado ice cream. Or you use bananas, nice cream. You should make it. Look it up, nice cream. That's what they call it. It's really good. You can all make your own. We actually had a churn off one year. So we made 3 different types. And so it was who could mix the fastest. And so one guy made it in like 20 seconds. So they had to have a team. Somebody's pouring the liquid nitrogen. And so we made 3 different types of ice cream. It was a really fun class. That was like 5 years ago. I think there were like 40 people in the class. It was 8th week. We needed something like that. So state our formula. Delta T equals K times molality, which is moles of the solute, over kilograms of the solvent. Where does the I factor in? The I factors in, so let's make a note here. The I is always multiplied by the moles of the solute. So anytime you see an I, it's going to go right here. That's where my I factors in. The way you'll find it in the book or online is they'll write the formula like this: delta T equals K, M, and I, which is fine, but then students get all confused. And so writing it like this makes more sense. It's the idea of what we just did down here. All right, that's 3 kilograms of water. That's my solvent. Our freezing point is -10. So reminder, if it's water or change, we're doing absolute value. So our delta T is 10 degrees Celsius. Our K is given to you, 1.86. It is different for every solvent. We're going to have X moles. That's what we're solving for. We have our kilograms. How many zeros is that? Make sure you write the right number of zeros. Kilograms of water. And then we put our I. I does not have a unit. It's just a number. You rearrange. You see that again today. So like the mole fraction has no unit. I has no unit. Pi has no unit. There's one other number out there that has no unit. Does anybody know what it is? It's not one we've seen today. All right, so you would divide by these 2 numbers and multiply by that, right? So you'll get X equals 8.7 moles. And that is of the sodium chloride. And then you just multiply by the grams per mole, which is like 58.5. And you'll get my answer around 510 grams of sodium chloride. All right.
Do you mind if you rearrange it really quick and write it out? I just want to be sure I'm understanding it right.
So you would do the 10 degrees Celsius. We would divide by the 1.86. we would divide by the 1.85, which has no unit. And then we'd multiply by the 3 kilograms. And that will equal our X moles. Is that what you're asking, Major?
Yes, thank you.
Yeah, okay. No, that's a great question, so thank you for asking. All right. I'm going to stop. Bye-bye.